We are now going to learn the basics of hypothesis testing. A hypothesis test is a standard procedure for testing a claim about a property of a population. For example, if a manufacturer of rechargeable batteries claims that the batteries they produce are good for an average of at least 1,000 charges or 1,000 hours, a sample would be taken for this claim. A statement or claim about a population parameter is called a hypothesis. To test the average of 1,000 hours, a pair of hypotheses are stated, one that represents the claim and the other its complement. When one of these hypotheses is false, the other must be true. A null hypothesis is denoted by the symbol H sub 0 or H sub O, and that is a hypothesis that contains a statement of equality, such as less than or equal to, or greater than or equal to. The alternative hypothesis, denoted by H sub 1, is the statement that the parameter has a value that's different. The statement has a parameter that is different from the null hypothesis. It is a statement that must be true if H of O is false and contains a statement of inequality, such as greater than, not equal to, or less than. To write the null and alternative hypothesis, we translate the claim made about the population parameter from a verbal statement to a mathematical statement. For example, a manufacturer claims that its rechargeable batteries have an average life of at least 1,000 charges. Since it says at least 1,000 charges, we are dealing with the average, which is the mu, has to be greater than or equal to 1,000. That is our claim. The alternative hypothesis, therefore, is the mean significantly less than 1,000. Another example is FIT College claims that 94% of their graduates find employment within 6 months of graduation. The population parameter now is a population proportion. So the null hypothesis says P is 94 hundredths. That's our claim. Alternatively, we want to say, is it different? So we have not equal to, the null alternative hypothesis, P is not equal to 94 hundredths. There are 3 types of hypothesis testing, and we're going to use equality for the null hypothesis, for the mean, and the population parameter. The left tail test, we're looking for the area on the left-hand side of the normal distribution, and therefore we think that the population mean or the population proportion is significantly less than the claimed proportion. For the right tail test, we're looking for the area on the right tail of the normal curve. Therefore, we think that the population mean or population proportion is significantly greater than the claim. And the two-tailed test just says the population mean and the population proportion is different than the claim, and therefore we're looking for an area either on the right-hand tail or the left-hand tail. This is a picture for a left tail hypothesis test. Notice the population proportion is in the middle over here, and we want to be able to determine if it's significantly less than the observed value. For the right tail test, we believe the population proportion is below the 0, and we're looking to see if it's significantly larger than that particular number. And for the two-tailed test, we're looking for the population proportion is in the middle, and we think it is definitely different than the given values. Now, when we are looking at the hypothesis test, we have to make a decision whether or not the null hypothesis is true or whether we're accepting it. So at the end of the test, one of 2 decisions will be made. Either we're going to reject the null hypothesis if we believe that the null hypothesis parameter is false, or we do not reject the null hypothesis if the information we have does not lead us to believe that there is a significant difference. And we say do not reject, just like in a court case, the judge tells the jury either to say that the defendant is guilty or not guilty. We never say innocent, and therefore we do not say accept, we just say do not reject. The 2 errors, therefore, is if we make the wrong choice. So a type 1 error occurs if the null hypothesis is rejected, when we later determine that the null hypothesis was true. Alternatively, the type 2 error occurs when the null hypothesis is not rejected, and we later find out that the null hypothesis was false and it should have been rejected. And here we have a chart that summarizes the information. So, for example, what kind of error could be made if the FIT College claims that 94% of their graduates find employment within 6 months of graduation. So a type 1 error would be what? That we rejected the null hypothesis, we rejected the claim when it is true. So basically the population proportion actually is 94 hundredths. A type 2 error would have been made if we failed to reject the null hypothesis. In other words, our answer was do not reject H of O. And later we determined that the population proportion is not 94%. Now, a level of significance. In a hypothesis test, the level of significance is the probability of making a type 1 error. The type 1 error is denoted by the alpha. The probability of making a type 2 error is denoted by beta. We will only discuss the type 1 error, which is alpha. By setting the level of significance at a small value, you're saying that you want the probability of rejecting a true null hypothesis to be small. Just because we set the alpha to be low does not necessarily mean that we will not reject. It just tells us that we're setting it at 10%, 5%, or 1%, and that is the probability of making a type 1 error. It doesn't mean that we will make a type 1 error. Now, with a test statistic is basically, these are the formulas we're going to use to calculate the z-score, the relative standing, or the t-score, which is also relative standing for the population mean, and we will discuss that in a future video. For example, a survey of 880 randomly selected adult drivers shows that 56% of those respondents admitted to running a red light. Find the value of the test statistics for the claim that the majority of all adult drivers admit to running a red light. Since we have a majority, that means 50% of all adult drivers, we would think would admit to running a red light. Therefore, we set our null hypothesis to P is equal to 50%. And alternatively, we want to find out if that population proportion is greater than 50%. So our test statistic is based on the 56% from the 880 adults in our sample. And therefore, we take our 56% minus the 50% divided by the standard deviation, which is the 50%, the square root of the 50% times the 50% divided by 880, which tells us we're a 3 56 hundredths of a standard deviation above the mean. Going to your Z table, you notice the area on the right-hand tail is quite unlikely. Therefore, we reject the null hypothesis, and we believe that there is a significant evidence to indicate that the true value of the population proportion is greater than the 50%. Let's talk about a critical region, or the rejection region. That is the set of all values of the test statistics that causes us to reject the null hypothesis based upon our alpha. A critical value is any value that separates the critical region, the area that we reject, from the values of the test statistic that don't lead us to reject the null hypothesis. Here we have a picture of a two-tailed test. The critical regions are on the left and the right-hand tails. A left-tailed test, a critical region is on the left tail, and a right tail, the critical region is on the right tail. Notice two-tail, we have the alpha divided by 2, because it could be either on the left-hand tail or the right-hand tail. In the example about adult drivers, we were using a one-tail test, which was the right tail test, and that is referred to the traditional method of hypothesis testing. The p-values means we want to be able to find the probability of the event occurring. And when we take the p-value of a hypothesis test, we want to find the probability of obtaining a sample statistic with a value as extreme or more extreme than the one determined from the sample data. The p-value of a hypothesis test depends on the nature of the test. Again, it could be a left-tail test, a right-tail test, or a two-tail test. And this type of test depends on the region of the sampling distribution that favors the rejection of the null hypothesis. The decision rule based on the traditional method is if the test statistic falls within the rejection region, we reject the null hypothesis. If it does not, we do not reject the null hypothesis. The p-value is basically comparing the probability to our alpha. And if the p-value is less than alpha, we reject the null hypothesis. If the p-value is greater than alpha, we do not reject the null hypothesis.